Now that we have defined Hausdorff measure, we can use it to define the Hausdorff dimension of a set. So let's consider a simple problem of comparing sizes of sets. So let's say we have a curve, so we have a square, and we have a cube. Okay, and let's say I ask you which one is bigger. Well, we have to sort of agree on what we mean by big in this case. All right, but this is what measures are for. So maybe we can pick an appropriate measure and compare the masses of each of these sets and use that to determine which are bigger. But which measure do we pick? So if we pick length measure, let's say h1, then if we look at the sizes of these sets with respect to h1 measure, the line segment, let's say, will have value between 0 and infinity, and then the square will have infinite length because essentially we can pack a infinitely long curve into the square. So it has infinite measure, and so will the cube for a very similar reason. So this tells us that this tells us that the line here is definitely smaller than the square and the cube. But as far as length measure is concerned, as far as one-dimensional Hausdorff measure is concerned, the square and the cube have the same size. Both are infinitely large. But we have no way of telling which of the square and the cube are larger if we just use one-dimensional Hausdorff measure. So similarly, if we use, let's say, three-dimensional measure, okay, now we see that the line has 0 measure, and so does the square. These have 0 volume, whereas now the cube has positive and finite three-dimensional measure. Okay, so now clearly the cube is the set that is larger than the other two sets. The other two sets have 0 measure, whereas the cube has positive measure. And so now, thus clearly the cube is larger than the other two. So notice that three-dimensional measure still treats the line and the square as having the same size, both being of 0 measure. But nonetheless, because we considered two measures, one-dimensional Hausdorff measure and three-dimensional Hausdorff measure, we were able to distinguish and order the sizes of these different sets. So the point of this example is that no one measure can help us compare the sizes of sets, since any Hausdorff measure will not be able to distinguish between its null sets or the sets that have infinite measure. So if we want to be able to come up with a way of comparing sets, not just lines or squares or cubes, but maybe more pathological examples, what ends up making sense is to not just consider two measures, but to consider the whole range of Hausdorff measures and use that to prescribe a notion of size to a set, which we will call dimension. So in the next slide, we'll make this idea a bit more precise. So let's first make the following observation. For a given set A, if it has finite s-dimensional Hausdorff measure for some value s, then its t measure will be 0 for all t strictly bigger than s. Similarly, if it has positive s measure, then it must have infinite t measure for t less than s. So we'll just show how to prove one of these properties. So notice that 1 is just the contrapositive of 2. So first of all, recall that hs of A is the increasing limit of the hs delta of A's as delta goes to 0. And so thus, hs of A is at least hs delta of A for all delta bigger than 0. Okay, so for a fixed delta, by definition of hs delta, there exists a collection of sets EI which cover my set A. They have diameters less than delta, and such that the sum of the diameters of these sets EI to the power s is less than hs delta of A plus 1. The number 1 isn't important, I just want it to be a constant. And furthermore, by the above inequality, this is always at most hs. This is at most hs of A plus 1. Okay, so these sets EI depend on the number delta. Okay, so now if we want to estimate the t delta measure of A, Well, we can use this same covering. This is a delta covering. We have a collection of sets EI that cover A of diameters less than delta. So that means that HT delta is going to be at most the sum of the diameters of these EI to the power not S but T. Now recall that the diameters of these sets are less than delta, which means that this is less than delta to the T minus S times the sum of the diameters of EI to the S. And then by the inequality of above, this is at most delta to the T minus S times the Hausdorff measure of A plus 1. Okay? And then recall that as I take delta to 0, that this quantity is going to converge to the T measure of A. But as we can see from here, because T is strictly bigger than S, delta to the T minus S will go to 0 as delta goes to 0. And thus, that implies that the T measure of A is equal to 0. So let's observe the following consequence of this theorem. So let's let S naught equal the infimum of all values S for which the S measure of A is finite. Okay, so by item 1, for all T values bigger than S naught, so if we're looking at the graph of the T measure of A, for all values T bigger than this number S naught, the Hausdorff measure of A is going to be 0. And also by virtue of this being the infimum of S, where the S measure of A is finite, that means that for all S less than S naught, the measure is infinite. Okay, so that means that for every set, the graph of Hausdorff measure looks something like this. There is a unique cutoff point below which the Hausdorff measure is infinite and above which the Hausdorff measure is 0. And it's this cutoff point that we define to be the Hausdorff dimension of the set. So to recap, the Hausdorff dimension of a set A is equal to the infimal value of S for which the S measure of A is 0. Or equivalently, it's the supremum of all values of S for which the S measure of the set is positive. So for example, D-dimensional Euclidean space, as the name suggests, has dimension D. Moreover, any singleton point has dimension 0. And in fact, any countable set A will have dimension 0. So one other version of dimension we'll discuss is Minkowski dimension. So you may have heard this under a different name of box counting dimension. So first of all, a bit of notation. For a set A and a positive number epsilon, we define NA epsilon as the smallest number of balls of radius epsilon it takes to cover the set A. So for certain simple geometric objects like line segments or squares, one can show that this quantity has some asymptotic regularity as epsilon goes to 0. In the sense that, for example, if we consider a line, okay, if we cover this by balls of radius epsilon, so let's say this line has length 1, one can show that NA of epsilon is approximately 1 over epsilon as epsilon goes to 0. Or if you look at a square, okay, and you cover it with balls of radius epsilon, then you can show that A epsilon in this case is approximately 1 over epsilon squared as epsilon goes to 0. So in each of these cases, we see that if we look at NA epsilon times epsilon to the S, then the limit of this as S goes to 0 is stable for some particular value of S. In the case of the line, it was S equals 1, and in the case of the square, it was S is equal to 2. Now, the idea of Minkowski dimension is to extend this idea to general sets by defining a dimension that measures how fast this number NA epsilon, so the counting number, grows as epsilon goes to 0. Or that is to say, what power of 1 over epsilon is this function growing like as epsilon goes to 0? However, it's not the case that there's always some unique value s for which this limit exists. So instead, Minkowski dimension is actually two different separate dimensions. Okay, so the first is the upper Minkowski dimension. So this is the infimum of all numbers s for which the lim supremum of Na epsilon times epsilon to the s is stable and equals 0. Alternatively, this is equal to the limit of log of the counting number over log of 1 plus epsilon. Okay, and then similarly, you can define the lower Minkowski dimension as the infimal s for which the lim inf of these values is equal to 0. Or alternatively, you can define it as the lim inf of log n over log 1 plus epsilon. It's clear that the lower Minkowski dimension is at most the upper Minkowski dimension, and one can also show that both of these are at least the Hausdorff dimension. But be warned that all inequalities here could be strict for a given set A. So why consider Minkowski dimension at all as an alternative to Hausdorff dimension? Well, one reason we like to work with Minkowski dimension sometimes is that it has a simpler definition and hence is easier to compute. And thus it can give you an easy upper bound on the Hausdorff dimension of a set. The disadvantage, however, is that the nature of Minkowski dimension is quite different from Hausdorff dimension, and sometimes it returns dimensions that don't coincide with what we think should be a natural dimension for a given set. So, for example, if we consider the set consisting of 0, 1, 1/2, 1/3, etc., then one can show that the lower Minkowski dimension of this set is 1/2. Whereas, this is a countable set, and hence its Hausdorff dimension is equal to 0. So this is not too bad an exercise to verify on your own. However, later on, we will see that the Minkowski dimension does give some nice results about dimensions of product sets. So we'll see that later on this week.